Okay, welcome, ladies and gentlemen, to the last lesson of Unit 2, dealing with limits and continuity. All right, so we're going to basically define continuity in a language that calculus people should understand. And we're going to look at one of our very first humongous theorems that you will see on the AP exam. Now, I'll get to that in a few minutes here. All right, let's define continuity at a point. You remember from previous math classes, continuity, myself included, most of your math teachers have probably said something along the lines of, as long as you don't pick up your pencil, the function is continuous. Well, that's not very high-level math worded, I guess is the way I want to say it. It's not worded very highly. But what we can say is, if we look at an interior piece of the function, just some random section of the function, a function is continuous at an interior point of C, or interior point C of its domain, some point along the line, because we like to say it's continuous at all points, and by this definition we can say it at any point C. Basically saying the limit of my function as x goes to c is f of c. So if we come along here and we have some graph, now we have a c value right here, right there, and here is f of c right here. It's basically saying as x goes towards c from either side, it's approaching a value of y that is f of c by plugging in the c into my function f of x. That shows that it's continuous at the interior of my domain. Something along this line, if I went up here like this and did that, there's c, I don't even know what the value that is, but the limit, and there's a dot here, that dot right there is technically f of c. So if we find the limit as x approaches c from both right and left, it's approaching a y value that is not f of c, and therefore it's not continuous on this part of the domain. Likewise, we can define continuity at an endpoint. This one gets a little confusing because an endpoint means something has stopped. But we can still do it, and the endpoint of some sort of interval. Basically saying the same exact thing. It's continuous at a left endpoint. That would be this one. This is the left endpoint test. And this would be the right. It's continuous at a left endpoint A or continuous at a right endpoint B if of its domain if as we approach x from the right-hand side, as we approach A from the right-hand side, meaning the left side, right? We'd approach from the left, or from the right, I mean, approaching the left. Then it's f of A, which means that dot, here's A, as we approach, f of A is at that dot. Or here, approaching from the left, f of B is that dot right there. In the same way we were talking about it over here with the continuity at a point. So one of the things that we want to be able to do is we want to be able to figure out if a function is continuous or not continuous. And interesting functions, you'll see an example here in a few minutes. There are some things you do need to remember. Types of continuity, or actually types of discontinuity. And the first one is removable. Now you might not always see these types of words, but a removable discontinuity is something like this, where a function is continuous, but there's a little open hole there, which means it's a removable discontinuity. You have a jump type of discontinuity. You have infinite discontinuity. Which means jumping over the asymptote there. And the weird one is oscillating. You can have actually oscillating discontinuity, like sine of 1 over x. Technically has discontinuity right there. It's removable, but weirdly removable. Okay. However, this function is continuous in other areas on the graph itself. Okay, some of our properties. These ones I wrote down. If you have two different functions, f of x and g of x, and they are continuous at x equals c, just as we defined a minute ago, then the following are continuous at x equals c as well. If f and g are continuous at c, then the sums of those two functions are continuous. The differences of those two functions are continuous, or the difference is continuous. The product is continuous, and a multiple or a constant multiple, so multiplying by k for any real k, that's also continuous. And the quotient is also continuous as long as g of c does not equal 0. And that should be obvious for us. We're going to use these here in a moment, or at least one or two of them. In this particular question, for a composition of two functions to be continuous, first of all, f must be continuous at c. So f has to be continuous at c. And g has to be continuous at f of c for the composite g of f. If you did f of g, then everything up here just switches. G would have to be continuous at c, and f would have to be continuous at g of c. So everything just switches if you switch f and g here. And here's a beautiful example of this. I want to show that this function is continuous. So first I want to show that it's the composition of two functions. And I can do that by saying, let's call g of x the absolute value of x, and let's call f of x the leftover stuff. So I can look at this and I can determine if it's continuous. First of all, we know that g of x is continuous, but that's not really what we want to know. We need to know, is f continuous for all values in this case? So we look at our properties. Our properties say that we can split it up. X sine x and x squared plus 2. Is the numerator continuous? Well, that's a product, so it's x and sine of x. Well, x always continuous. For every value of x, that function is continuous. Likewise for sine, that is a continuous function. And then x squared plus 2. Is x squared plus 2 a continuous function? Yes. Will x squared plus 2 ever equal 0? The answer to that is no. X squared plus 2 is always above the x-axis. So it's never 0. It's never negative. Negatives don't matter. But it's never 0. So we can follow that last f over g on the last page, that last slide. So since f of x is continuous, can't spell right now, continuous, and this function is continuous for all values of x, therefore this function is continuous. We showed that the inside piece is continuous, and since that's continuous, g of x is continuous everywhere for the absolute value of x, and therefore it is a continuous function. All right. This is our very first ginormous theorem. This is the intermediate value theorem. It gets its own page. It gets its own acronym, IVT. It's not a very special acronym, but it's the IVT, the intermediate value theorem. It's only chapter 2. It's only the first little stuff of calculus, and we've already got something that will show up on the AP exam. And here's what it says. A function y equals f of x that is continuous on a closed interval a to b takes on every value between f of a and f of b. So the question is, what the heck does that mean? If I was to look at a graph, we're looking at the interval from a to b. And let's just say I randomly created some sort of graph. Oops, I don't like that graph. I'm going to change that graph. There's a reason for it. Okay, let's try that again. Let's draw something a little bit better. Okay, I like that graph better. Okay, we are saying that this function is continuous between a and b, inclusive. What this says is the function takes on every value. Here's f of a, and here's f of b. What this is saying is every value between these two numbers will be used on a continuous function. So if f of a was equal to 1 and f of b is equal to 7, every number between 1 and 7 will be a y value on this graph. And it's also likewise saying, this is written out, but I have my graphs in the way. This is also saying if I have a c value between a and b on a continuous function, that guarantees f of c is on this list somewhere. So let me erase my graph. I'll draw it a little bit better here in a minute if I need to. So if y0 is between f of a and f of b, then y sub 0 is equal to f of c for some c. Okay, so I said it backwards. I always do that. I always accidentally do that. Here's f of a. Here's f of b. And here's a. And here's b. And let's just create a random graph. Something along the same lines. If you have some value here that is f of c, it guarantees that c is between a and b. But this is a theorem, and theorems usually go in both directions, which means there will be some sort of c value in here that will make f of c between f of a and f of b. That's how it has to work. So a question that I could ask is something along this line. It's usually, we call it kind of an existence theorem, because all it tells us is there is something there. It doesn't actually tell us how to find it. And students usually have struggles with existence theorems because they want to do something with them. But you have to understand, existence theorems just tells you that it has to be there. So this is the type of question that this could be said. Is there a number that is exactly 1 less than its own cube? Okay, so we do a little bit of algebra and we get this. And if we were to graph this function, I have it graphed in front of me here, it would look a little bit something like this. Okay, something like that. What it's asking is there a number that makes this a true statement? It doesn't ask what that number is. Now, technically, yes, we could solve this, whatever. But you notice right here at x equals negative or positive 1 and x equals positive 2, you notice how it crosses the x-axis. We're looking for, is this function 0? Well, graphically, yes. At some point in time between 1 and 2, it will be 0. You could also say f of 1 is 1 minus 1 is 0 minus 1 is negative 1. It's negative 1. So it's negative, and then f of 2 is 8 minus 2 is 6 minus 1 is 5. And because it changes sign, using the IVT, okay, so f of 2 is negative 5, or sorry, positive 5, and f of 1 is negative 1. And because it changes sign, by the IVT, f of some value equals 0. So the answer would be yes. Because it changes sign, there has to be some y value between negative 1 and 5. That's going to finish us off for the day. I'm going to leave you with this. Hopefully you don't come in thinking that this relates to you, but I will see you guys tomorrow.